Hi guys, today I want to show you boost converter switching power supply. I want to order this model because I want to use it to charge my Vespa PX battery from a solar battery. Unfortunately, the module I used previously didn't have a current limit and broke due to excessive charging current. This module here is advertised as a 400 watts boost converter with 15 ampere input current. I wonder if that's true, but I don't need that much power anyway. The lowest input voltage is plus 8.5 volts. The highest achievable output voltage is plus 60 volts. My solar battery has a nominal voltage of plus 11.2 volts. That's significantly more than the minimum required plus 8.5 volts. So that's fine. And the charging voltage for the lead acid battery should be the plus 13.8 volts. That's significantly less than the maximum possible plus 60 volts. So the module should easily manage that. Therefore, I can order the module. You can find the link in the video description. The module has arrived. Let's see if we can see anything that was damaged in transit. I can't find anything serious. That's wonderful. Let's take a look at the components used. The module has two terminal blocks for the input and output. The cable openings seem a bit small for 400 watts, but let's see. I like the large CAN capacitors. They can certainly handle more ripple voltage than the usual SMD capacitors. And 220 microfarads, 63 volts. Oh, and even a plus 105 degrees Celsius rating. That sounds pretty good. But to be honest, I'm skeptical about the maximum voltage rating. Unfortunately, the value given is often too high. A 15 amp fuse was installed at the input. That's very good. I haven't seen that on any other module before. Here we see the toroidal coil. It's neatly wound, and the wire diameter also looks trustworthy. The advantage of the toroidal core is that the magnetic field is strongly concentrated in the core. This increases efficiency and prevents disruptive stray fields. Then we see large heat sinks, each with a leaded component mounted on it. The assembly is electrically isolated. I like that. The lower component is an 85 volts 80 amps MOSFET transistor type NCE8580, and the upper component is a 20 amp Schottky diode of the type MBR2100 CTD. The two small black components in the SOT93 package form the totem pole driver for the MOSFET. This allows the MOSFET to be switched on and off quickly, drastically reducing switching losses. the IC is TL494. This is a PWM control IC. This determines the switching frequency and controls when the MOSFET should be switched on or off. It even has the voltage reference integrated. Really good. Yeah, the component with the marking R010, yeah, we have it now, is the measuring resistor for current measurements and has a resistance of 10 milliohms. And the upper blue component here, labeled W103, is a precision trimmer. This can be used to precisely adjust the output voltage later. And the lower blue component, labeled W502, is also a precision trimmer. This can be used to adjust the current limit value later. And yeah, the quality of the solder joints is, as almost always, good. And yeah, the fact that the toroidal core has no additional mechanical fastening means that the module should only be used in stationary operation. This doesn't apply to my application, but it could have been solved more sturdily. And yeah, the board has mounting holes so that the module can be securely mounted, for example, in a housing. That's really good. The underside shows that the heatsinks are securely attached to the board with screws. The conductor tracks that carry a lot of current are also nice and wide and short. This reduces losses. By the way, the energy flows in a two-stroke process during boost conversion. First, the coil's magnetic field is built up, then the coil discharges via the diode.
Then let's test the module for its maximum load capacity. So a suitable stranded wire with a cross-section of 2.5 square millimeters won't fit into the terminal block. No chance. I checked again to see if other offers of this module on Aliexpress have better terminal blocks, but they all seem to have the same terminals for 1.2 square millimeter wires. Soldering is the more reliable connection anyway, so I will solder the wires on now. Of course, I have to remove the solder mask first. I checked the module's specifications again. The realistic maximum input current is 8 amperes. At higher currents, the module would quickly overheat. So this is something to be absolutely mindful of. My 13 volts 22 amperes power supply serves as the power source. My self-constructed current sink circuit serves as the load. Should I make a video about this? The trimmer that sets the current limit must, of course, be turned to the maximum for this test. Clockwise here. I set the module's output voltage to plus 24 volts. I set the current sink so that the input current is just under 8 amperes. With an input voltage of 13.2 volts and an input current of 7.7 amps, the output voltage is 24.15 volts with an output current of 3.94 amperes. The current is calculated from the shunt voltage of 19.7 millivolts divided by the shunt resistor of 0.005 ohms, which is included in the current sink circuit. This results in an overall efficiency of 93.62%. A very good value. The Schottky diode heatsink gets hot. This shows why more input current shouldn't flow. The transistor heatsink, on the other hand, only gets slightly warm. The output power was 95.2 watts. That's far from the advertised 400 watts, but we already knew that, right? From previous tests, I know that the maximum output power is 240 watts. However, this is only achieved at higher voltage levels, e.g. when converting from 24 watts to 60 volts, because a current of 4 amps at 60 volts allows for higher power. Let's test how high the ripple voltage is at maximum load. An input current of just under 8 amperes flows again. I'm setting the oscilloscope to AC coupling since we are only interested in the ripple voltage. Wow, that's a strange signal. The pulses have a peak-to-peak voltage of 476 millivolts. Based on 24 watts, that's about 2% ripple. That's a bit high. Let's take a closer look at these pulses. We are seeing what's known as ringing. That's a decay of the resonant circuit consisting of inductance and capacitance. This always happens when the coil is fully discharged during the discharge cycle. Another indication that we are at the limit. The ringing frequency is 58.8 MHz. At an impedance of 6 ohms, 476 millivolts peak is almost 80 millivolts peak of RF transmit power. The interference is so strong that it's even interfering with my DSO. The module urgently needs an interference filter at the output. Otherwise, there will be serious interference in the surrounding area. It also helps to mount the converter as close as possible, maximum 30 centimeters away, to the load. Short cables emit less EMI. It would also be interesting to see if the ringing only occurs at full load. I'm now reducing the input current to approximately 4 amperes. as you can see, the output voltage still rings. So it's no use. I definitely need a noise filter, like every user of this module. To tame the interference, I'm making a small noise filter myself. I have a commercially available ferrite ring suitable for noise suppression. This is wound with an enameled copper wire, 66% of its circumference. The noise filter circuit looks like this. Now the whole thing is mounted on a small perforated board. The exciting moment is coming soon. Will the noise filter effectively suppress the high-frequency ringing signal? Yes, indeed, it does. The ringing is no longer visible. Now you only see the switching ripple voltage. Now that's a complete success. Now I can use the module to charge the lead-acid battery with a clear conscience. All I have to do is set the maximum output current to 1 amp and connect a diode in series on the positive wire at the output. The links to the products I use are in the video description. That was another informative video. I think I deserve a like, a positive comment, a subscription and a donation. Until the next video, bye bye.